So we're gonna go on a journey. The journey includes an equation from Ismail's book. It includes the Q gamma function, and the star means that the brackets are related to the same function. And we're gonna calculate a value for this. And the information we're gonna use is the gamma function at a half. It is equal to this, and we're going to also use the information that the Jacobi theta function, the second Jacobi theta function, is equal to 2 times the Dickin eta function to the second power of 2 tau, and the Dickin eta function of tau. And here Q is it's the norm with either the I pi tau. Okay, and this is the definition for Q gamma function. Okay, well, let's dive into this, shall we? Now we're gonna do a first test to see that we are sane, that we have a rational mind, and we're not going to go insane by delving into this problem. So to check that we're sane, we're gonna use the case where a equals 0 and b equals 1. And intuitively, you can see why this is the same case. Sorry. Because this is going to be 1. Here, this is going to be 1. And these two are going to cancel these two. So what we're left with the integral from 0 to infinity of t to the power of s minus 1. And here, if you go from 1 to infinity here, the first one, the q, it's just going to be q to the power 0, so 1. And here, if you place 1, this is going to be 1. It's going to start from 1, and q to the power of 1, q to the power of 2. So these, of course, these two will cancel out because a is going to be 0, so it's going to be the same thing. But from here, it's going to cancel out every single of the factors except from when here q to the power of 0. So you'll get 1 plus t dt d tau or t. But what makes this interesting is all of these will cancel out, except this is going to be 1. So with ones, we don't really care about ones. They can be whatever. But these two, they have nothing to cancel out on. So we will just be left with the gamma function of s times the gamma function of 1 minus s. And this is a famous result. Like, this is one of the most famous Mellin transforms, and yeah, it's pretty famous. And I think that this at least cleared some of our insane ideas. I know, we can settle down now and go to some more interesting examples. Okay, let's do some more challenging example. So I'm gonna add a few more definitions. So with the Q gamma function, you can do an addition formula like this. And the reason is because, I did an example here, is because if you just add integers, for example, it just starts, it has a couple of first terms that are different, but then it starts the same. So if you want to get the other one, you will just have to do a product with these so that it cancels out. And the first term also, you will have to get those to be similar, but I will get to those. First we'll need to okay, well this is what we're going to basically calculate. Is we're going to calculate this integral, and we're going to calculate it by calculating certain Q gamma functions and certain gamma functions. But gamma functions, their values are quite trivial. I guess the value that we are going to calculate is trivial because basically you can already see this can be half, and we know from Gauss, it's the famous Gaussian integral. We know the value of the Gaussian integral. It's one of the most famous results in mathematics. But let's see the statement that we're going to make for problem number 1, and then we're going to calculate the values for it. Okay, so the statement is that we're going to calculate the integral from 0 to infinity of 1 plus q, and since a is 3 halves, we're going to get for the first one it's going to be 1 plus 3 halves, so 5 halves over tau t, and the second term is going to be 1 plus q 7 halves, and the next one is 9 halves, and so on. But see here, since b equals 1, we're going to get quite similar result as the last example, where almost everything cancelled out except, okay, we're going to do t dt. Almost everything cancelled out except the 1 plus t, and the similar situation is going to happen here. And something fun is going to happen also. We're going to get 1 plus q times 1 plus q to the power of 2, 1 plus q to the power of 3 cubed. And so, okay, so this is the integral we're going to calculate, where q is e to the power of minus 4 pi. Isn't this so interesting? Like, why are we calculating values to integral like this? But the interesting part is going to be, since we're going to as e equals half, so the first gamma functions are just going to be half squared, and a equals 3 halves, so 3 halves plus half is 1, so that's going to be 1. And the reason it's going to be 1 is because if we put 1 here, this is going to be just 1, and these are going to cancel out. Okay, so b equals 1 as equals a half, so we're going to get q gamma function of half. But see here, since these are both going to be half, one of them is going to cancel out and one of them is going to remain, and a plus b is going to be similar as here, it's going to be 5 halves. So we're going to get gamma function of half times the gamma function of 5 halves. And okay, so now we just need to calculate what this is. But this is quite simple actually, since gamma function of a half is square root of pi, its squared is just pi. Okay, well that's quite simple. But the q gamma function of a half, that's going to be a bit more interesting. We're going to need to calculate it, and since q is e to the power of minus 4 pi, we're going to get quite an interesting value here. So let's calculate the gamma function of e minus 4 pi of half. It's going to be, and I'm just going to calculate everything down here, and then I'm going to place the value here. So we're going to get a final result that's going to be quite awe-striking. So it's going to be square root of 1 minus e to the power of minus 4 pi. And then we're going to get, since that's 1 to the 16th, we're going to get e to the minus pi over 4. Okay? And the Dedekind, the Jacobi theta function, the second Jacobi theta function, it has a value of a Dedekind eta function. And since these are quite well known, the values of Dedekind eta, thanks to Ramanujan, who actually did the surprising work of discovering the values of Dedekind eta, which were quite surprising at the time to people. Like, how could you actually calculate values to a function like that? But we need to calculate the value of the Jacobi theta function, the second Jacobi theta function of the gnome e to the minus pi, basically, which is going to be the simplest thing to calculate, because these are also the simplest values to calculate. So it's going to be 2 times, now this is the Dedekind eta function of 2i. So it's going to be pi to the power of minus 3/4 times 2 to the power of minus 11/8, and then the gamma function of 4. Okay, and that's going to be squared, and then the Dedekind eta function of I, which is going to be pi to the power of minus 3/4 times 2 to the power of minus 1, and then a gamma function of 1 to the 4th. And these are, we're going to get one gamma function of 1 to the 4 at the top, and this is going to be 4. One of the pi to the power minus 3 to the 4 is going to cancel out, and 1 is going to be left at the top. So we're going to get, and basically we're going to think of that as 16 to the 8. So basically we're going to be left with 2 to the power of 5 over 8 times pi minus 3 over 4, and gamma function of 1 over 4. Okay, now we have calculated values this. We know what this is. Now we just need to know the value of 5 over 2. But that's going to be simple because we know here what it's going to be, since we have this addition formula. Okay, so let's see how the addition formula is going to play out. So we're going to get, let's do it by Q first, and then we'll add the values beforehand, or after we've done this, sorry. Okay, so we're gonna, first we're gonna get 1 minus Q 3 over 2, and that's gonna be over 1 minus Q, and then we're gonna get 1 minus Q half over 1 minus Q, and then we're going to get exactly the thing we calculated value to, and these are quite easy to calculate. So, and to the people who want all the details, here are the details, how it works and why it works the way it does, and all the nitty-gritty details of people who like details and so on. But basically, this is going to be, this is almost going to be it. Now we just need to plug all of this in. And we can basically okay, let's do it like this. So the values are going to be 1 minus e to the power of minus 6 pi. So I'm doing these first because we're gonna get gamma function of q gamma of a half to the power of 2, so we can just place that to the end equation. And here we're gonna get e to the power of minus, it's gonna be minus 4 pi, it's gonna be minus 2 pi, and then we're gonna get to the top, we're gonna get 1 minus e to the power of minus 4 pi squared. So if that's not visible, there's be a squared there. And I'm gonna, okay, so, and then we're gonna get q gamma function of e to the minus 4 pi of a half. So this is almost our final result. So I'm gonna type all of this out in an empty paper so we can see the final result and marvel the beauty of it. Okay, here's the final result, and this is gonna be a lot, so bear with me, please. So here's the integral we calculated. What is this? So basically the sum of 1 plus e to the power of minus 10 pi over t, tau, and times minus 14 pi, minus 18 pi, and it increases by 4. And this starts by minus 4, e to the power of minus 4 pi, minus 8 pi, minus 12 pi. So the power is 4, basically. And you can see that this is not power of 4, but it is, this is 2 times 7, 2 times 9, and so on. So it's like odd, 2 times an odd number, starting from 5. And the interesting part is, why is 1 minus e to the power of minus 4 pi, why is it squared? And yeah, I think that's an interesting question. But this is basically the final value of what we get, of going all of the deep details of it, what this entails. And this is interesting because it's an integral of an infinite product of a value of something. And for basically the help of Ramanujan, Ismail, and yeah, this is a lot of combined mathematics that helped us calculate the final value. And there's a lot of questions to be asked. Why is it like this? Why is 2, 6, 8 there and 4 there? And why is there a gamma function involved? But now the questions are to be asked. People can ask questions now and try to answer them. And I'm gonna calculate other values to some other cool functions, maybe like boson propagator in string theory. It also has like Jacobi theta function alternative for the brane space. So that's gonna be interesting, but I'll calculate those later. This is for now, and hopefully that's cool enough for today and made you interested in mathematical thinking. So yeah, that's gonna be all for today, and I'm gonna do um I'm gonna just say that you know um have a great day and eat a pie and so on. Okay, goodbye.